In this video, we will be talking about chain drives and belt drives which fall under the category design of mechanical transmission system. The content which is going to be covered in this video are concept explanation, application of the topic, formal design procedure and also an example problem for both the topics. To start with chain, what is a chain? A chain can be defined as a series of links connected by pin joints. You will be seeing how the links are joined with the help of pins later in this video. So now that we know what is a chain drive, what is it going to be used for? Chain drives are a means of transmitting power, like gears, shafts, and belt drives. Chain drive comprises of four main characteristics. They are high axial stiffness, low bending stiffness, high efficiency, and they are relatively cheap. Depending upon the application, there are various types of chains. Conveyor chain. It supports weight as the roller can support along the surface, hence it can be used for transporting materials. Inverted tooth chain. It has sprocket teeth mesh with shaped links. Instead of roller on chain, the overall effect is to reduce the noise. Leaf chain. Used for lifting rather than power transmission. Heavy duty chain. Widely used in applications like a roller coaster. Before we get into video, in any motion control system, the objective is ultimately to move some kind of load. The component in the motion system that converts electrical energy into mechanical energy is the motor. But the task doesn't end there. A motor output shaft has to connect somehow to whatever the load is. Some of the most efficient ways to connect the load are so called direct drive methods, where the motor is directly coupled to the load. When this isn't feasible, various intermediary methods are available to couple the motor to the load. One of these is a roller chain. Coming to the construction of roller chain, there are five major components which make up the roller chain. They are the inner link, the outer link, the roller itself, bush, and pin. The pin is press fitted to two outer links while the bush is press fitted to inner link plates. The rollers are safely fitted on the bush. The links are usually made up of medium carbon steel and the pins, bushes and rollers have a HRC value of about 50. So this is a simple chain. This chain is called a duplex chain. So the roller chain when connected with two shafts, one becomes the driver and the other is called the driven. Since you have learned a few basics, let us see how a roller chain is being used in a practical application. In this video, the application is chosen wherein in an airport or an industry, a petrol engine of 10 kW is connected by a shaft to a load which is the conveyor belt. The shaft of the engine is called the driver which runs at 900 rpm and the shaft on the conveyor is called the driven which runs at 235 rpm. Let us now see the design procedure and how they are used to solve a problem. So the problem statement here says that it is required to design a chain drive to connect a 10 kilowatt 900 rpm petrol engine to a conveyor. The driving sprocket is mounted on engine shaft. The driven sprocket is mounted on conveyor shaft. The conveyor shaft should run at 235 rpm. The service conditions involves moderate shocks. The center distance is 780 mm. Before we could get started, the standard values and the approximation values are referred using PSG design data book. So the given values are power, speed of driver, speed of driven and center distance. The first step is selection of transmission ratio which is indicated by the alphabet I. I is N1 by N2 which is 3.82. So from design data book page number 7.74 we can standardize the value as 4. The second step is selection of number of teeth on driver, that is Z1. So Z1 is taken as 25. Since the transmission ratio I value from here is 4, we have taken 25 since this is the maximum number. So the third step is selection of number of teeth on driver on driven, that is Z2. So that is the formula for that is Z2 is equal to I into Z1 where I is 4 and Z1 is 25. We get it as 100. It's taken from page number 7.74. Step 4 is selection of standard pitch, that is indicated by letter P. So in this problem we have assumed the chain to be 10B3TR1595, that is this one, which has a standard pitch value of 15.875. But since we know the center distance A, we can also calculate with this formula where Pmax and Pminimum are A by 30 and A by 50, where the maximum pitch lies between 15.6 to 26. So we've taken as 15.875. Calculation of total load, which is sigma P, is the sum of PT plus PC plus PS, which so here is the formula. And all the three formulas have the standard value kgf. So hence we calculate the total load in Newton. Hence the conversion of kgf to Newton we need to multiply into 10. So PT means tangential force due to power transmission. So the formula is 102 into N by V, where V is the velocity and N is the power in horsepower, which is taken from here. So V is Z1 into P into N1 by 60, where we get 5.95 meter per second. So we substitute this 5.95 instead of V, and here since the power is 10 and this 10 is used because we need to convert kgf to Newton. So we get the value 1714.28 Newton. So PC means centrifugal tension. So the formula for that is W into V square by G, where W is taken from the table here, that is 2.73. So the answer is 96.64. So PS is the tension due to sagging of chain. So the formula is K into W into A. Here we assume K to be 6 since it's going to be horizontal, and W is taken from this table 2.73, and A is the center distance, which is given at 780 mm. We get 127.76 Newton. So summation of all this is going to be the total load, that is 1938.68 Newton. So step 6 is where we calculate the service factor as indicated by alphabet KS. Taken from DDB 7.76 is where we assume the values. So KS is K1 into K2 into K3 into K4 into K5 into K6, where we have assumed all these following assumptions, where K1 is the variable load because in conveyor there won't be any constant load. The load will keep varying and it's an adjustable support. I've taken K3 since we've calculated the pitch from using the formula A is equal to 30 to 50p, and inclination of the line joining the centers of the sprocket to this is going to be horizontal up to 60 degree, and the lubrication is periodic lubrication and it's continuous running because it's going to be running in big airports and also big industries. So the KS value stands to be 2.815. Calculation of design load is sigma P into KS, where sigma P is the total load and KS is the service factor. We get the design load to be 5457 Newton. So how do we calculate factor of safety? Factor of safety is calculated using braking load by design load. So how do we get since we know the design load is here, how do we calculate the braking load? It is taken from the standard book, the design data book, where braking load is 6810, but since we know the design load is in Newton, we need to multiply by 10. So that's why it's 6810 into 10 by the design load. We get it as 12.47. Since we have the working factor of safety, we need to find out the minimum factor of safety. That lies to be 11, which is less than the minimum. So since a working factor of safety is greater than the minimum factor of safety, our calculation or our design procedure is safe. So in step 10, we calculate the bearing stress, where the bearing stress formula is PT into Ks by A. The formula, so the value is 21.8 0.00 Newton per mm square. We need to compare this with the allowable bearing stress, which is also the maximum bearing stress. We take it from the table DDB 7.77. So our allowable bearing stress is 22.4. Why is it here 2.24? So this value is calculated when people use kg pound, but since we use Newton, it's multiplied by 10. So since my bearing stress value is less than the allowable, our system is safe. So calculation of length of continuous chain, that is indicated by L suffix p. The formula is this, which is taken from design data book here. Since we know, so in this we know all the values except for AP. So for AP there's another formula, that is A naught by P, where A naught is the initially assumed center distance, that is 780, and P is the pitch. So by calculating we get 49.13, and we put this 49.13 here, and we get the length of continuous chain to be 163.66 mm. And calculation of exact center distance, that's A. The formula is E plus root of E squared minus 8m, so everything is under root by 4 into P. This is the formula. In this, E and M are not known, so there's two more formulas for it. Those are these two, and the value lies to be 101.5 and 142.48. And since by calculating modulo it comes 142.48, but we use the standard values which is taken from DDB 7.76, that is 142.90, since so that it's rounded off. So this 142.90 is here, and we calculate, and the value to be is 782.64. So here the chain also has a sagging length, so that has to be calculated. So the formula for that is 0.5 into F, and F has the another formula 0.02 into center distance. So this is the one from DDB 7.75, and the value calculated to be is 7.80. So the actual real center distance is A minus A sag, that is 774.81 mm. So calculation of the length of the chain, so this is continuous length into pitch value, that gives us 2603.5 mm. That should be. So in step 15 we calculate the pitch circle diameter and outer diameter, that is D1, D2, D01 and D02. So the formula is that P by sine 180 by Z1 for small sprocket and Z2 for large sprocket, and the values are 120, 126.66 and 505.40. And outer dia of small sprocket, the formula is D1 plus 0.8 into dr, and for D2 similar D2, and dr is obtained from here, from this value 10.6, so it is obtained to be this one. So since that we've calculated all the dimensions, we need to represent it in a diagram. So this is how our roller chain looks, and this is the spacing, this is the center distance. We found it out to be 774.81 mm. This is the pitch 15.875, and this is the diameter of small sprocket D1, and this one is the large sprocket, and this is the outer dia. So the difference between dia of small sprocket and outer dia is that outer dia is calculated end to end, that is from this tip to this tip, but in case of dia of small sprocket the tip is not calculated, it's just the inner part. So this same applies to this as well.
Moving on to flat belt drive. We use flat belt drive to transfer power from one shaft to another, which these shafts are separated by some distance. It consists of a driver and a driven pulley. When the belt is rotating in a clockwise direction, and this drive is said to be in forward motion. Under this forward motion condition, the upper part of the belt will always experience a sag. It's not always, will experience a sag. This sag is nothing but the upper part of the belt will experience compression, and this side is said to be a slack side. And the lower part of the belt, when the drive is in forwarding motion, is known as tight side. And this part of the belt experiences tension while the upper part experiences compression. In belt drive, the power transmission depends upon the amount of friction between a pulley and belt. It means that when the friction is high, the power transmission is efficient, and it's vice versa in the opposite case. The slip can be eliminated by running the belt with slower speed. Why do we use a flat belt drive? So there are multiple reasons, and we can see some of them. So it produces comparatively low noise. We do have flat V belt drive and a flat belt drive. When comparing with the V belt drive, flat belt produces low noise, and when the application is in a horizontal position, then the power transmission will be efficient while using a flat belt drive. They are relatively cheaper, and the distance between two shafts is larger, and the suitable drive is flat belt drive. You can see a list of applications here, but more lively. Let me quote you a good example. Many of you have been visited to a grinding shop, where you give spices and they grind these spices and give you as a flour. These grinding machine will always be operated with the help of a flat belt drive. Before starting this grinding machine, they'll start a motor, and then they'll connect the flat belt drive to this motor, and which transfers power. So the power from motor is transferred to the grinding machine, and it starts to grind. So our problem statement. And for designing a flat belt drive, we use design procedure of 7-step design procedure. We are going to design a flat belt drive for the following data: AC motor which is operating at a speed of 1440 rpm and operates for over 10 hours. And the equipment driven is a compressor which runs at 900 rpm, and the required power transmission is 20 kilowatt. Step 1 for the design procedure is calculation of pulley diameter. So for calculating the pulley diameter, we all know the velocity ratio, which is nothing but N2 by N1 is equal to the diameter of larger pulley divided by the diameter of smaller pulley. So keeping on this formula in mind, we are calculating the speed ratio, which is nothing but the speed of driver divided by the speed of driven. The ratio is 1.6, and using power torque relation, we obtain the smaller pulley diameter, which is nothing but 265.3 mm, of course. And then the larger pulley diameter is obtained by multiplying the speed ratio along with the diameter of smaller pulley, which is nothing but 424.5 mm. What we found is just a value, and which is not a recommended value. We don't know it, and we are going to find this recommended value from design data book page number 7.54. For your kind information, we are using design data book from published by PSG, and in the page number 7.54 we can see this table, recommended series of pulley diameters and tolerances. And from this table, an arc diameter of smaller pulley is 265, and we are not going to take value or recommended value which is less than this, but we are going to take a value just a step greater than this. So then the value should be 280 mm for smaller pulley, and it should be 450 mm for larger pulley. Step 2, which is nothing but the calculation of design power. From the problem statement, we know that the power required for the compressor to run or to operate is 20 kilowatt. And before calculating the design power, we need a series of or a set of values which is to be found out. Starting on with the load correction factor. We know our load is compressor, and you can see this table in design data book 7.35, and for this load, and the load correction factor is 1.3. So the load correction factor is nothing but Ks. And the next value to find is K alpha, and before finding K alpha, we need the arc of contact. For finding arc of contact, we need center distance and we are going to calculate center distance with this formula. And we found out the value of diameter of larger pulley and also the diameter of smaller pulley. Substituting the value, and we can find the center distance as 1500 mm. Substituting these values in arc of contact, we can find the arc of contact value as 173.2 degree. From BDB 7.54, we can see this table. The arc of contact is 7.3, 173.3 degrees, and I'm not going to take value which is less than 173, but it should be greater than 173, and the next in immediate next value is 180 degree, and the correction factor is 1, and this correction factor is nothing but K alpha, and which is required for calculating the design power. The next is the small pulley factor. The small pulley factor depends upon of course the diameter of smaller pulley. Our diameter is 280 mm, which is in the range of 200 to 300, so the value is 0.7. When the diameter lies between the range of 100 to 200, it is 0.6. When it is in the range of 300 to 400, it is 0.8. And substituting the found values in the formula, we can see the design power is 37.142 kilowatt. We found out the design power. The next step is the selection of belt. For that, we are finding belt velocity or the belt speed in terms of velocity in meter per second. The diameter D here is nothing but the smaller pulley diameter in meters, but not in millimeter as we normally use, because the velocity we are finding out should be in meter per second. And from design data book 7.54, you can see these equations, and why we are finding out these equations, we are seeing or we are referring these equations is nothing but to calculate the load rating at 10 meter per second. We are assuming our flat belt drive is a high speed flat belt drive, and you can see the high speed 878 G duct belting, and for this we have two values. One is in kilowatt and another one is in horsepower, and we are taking in the value in kilowatt, 0.023 kilowatt. So the load rating at 10 meter per second is 0.023 kilowatt. Moving on to step 4. The step 4 is load rating correction. We have found the load rating at 10 meter per second, but our velocity is not in 10 meter per second but some value higher. So in the formula 0.023 multiplied by V divided by 10, we are substituting our velocity, and the corresponding load rating at V meter per second is 0.0485. The next step is to determine the belt width. To find belt width, we need design power, load rating, and the number of ply. We already know design power and load rating. The remaining is the number of ply. To calculate number of ply, we are going to refer design data book page number 7.52. You can see this table, the minimum pulley diameter table in design data book 7.52, and calculated speed, belt speed for our problem is 21.111 meter per second. So the maximum belt speed we are taking here is 25, not 20. You can see because our value is 21, and we are going to take value higher than the 21.111, which is 25 here. And the pulley diameter is 280, and in the series of 25, you can see 140, 200, 315, 400, and 630. You can't take 200 because our value is 280, and we are taking 315, which is a higher value than 280. So the number of ply respecting to these values is 5. And in the same page number, so design data book 7.52, you can also see this table. So what we found, the value of belt width is 153.16 mm, which is not a standard value, and we're going to find the standard value in this table. We can see the number of plies listed over there and for each ply there are standard belt width. And our number of ply is 5, and what we calculated belt width is 153 point something. So for that 153 point some decimal value, the number of ply, you can see the series of values 76, 90, 100, 112, 125. But the nearest value for our calculated value is 152. So the standard value and also the belt width is 152 mm. So step 6, the last before step of our design procedure, is nothing but the determination of pulley width. The pulley width is calculated by addition of 25 plus belt width. So this factor 25 is decided by, of course, the design data book page number 7.54. You can see this table, and from this table our calculated belt width is 152. So the belt width is above 125 and up to and including 250, and for this the pulley to be wider than the belt width by 25. So the pulley width is 152 plus 25, which is 177. And again, and what we calculated is not a recommended value. We have to choose a recommended value from design data book, and in this page number 7.55 you can see the recommended series of with the flat pulleys. So the recommended series nearest to the value of 177 is 180. So from the table the recommended value of the pulley width is 180 mm. The last procedure, design procedure, is a calculation of length of the belt. So the next assumption we are doing in the whole design procedure of 7 is nothing but assuming it as an open drive. So in design data book 7.53 you can see this table named as belt length, which has 3 formulas, and we are assuming our belt drive is an open drive. So we are taking the first formula. We know the value of center distance and the diameter of larger pulley and the diameter of smaller pulley, and substituting the values in this formula, and we can find the length of the belt is nothing but 4151.49 mm. So we have successfully finished or completed our design procedure. Thereby we have designed a flat belt drive for a respective problem statement. I hope you all understand our video and the concept of chain drive and flat belt drive. Thanks for watching.